Hello there, and welcome to a journey that will take you deep inside one of Earth's most powerful and awe-inspiring natural phenomena. Tonight, we're going to explore volcanoes, those magnificent mountains that breathe fire and reshape our world. From the depths of the ocean floor to the highest peaks on land, from ancient eruptions that changed history to the quiet giants sleeping beneath our feet, we'll discover how these incredible forces of nature work, why they exist, and what makes them so fascinating. Imagine standing near a volcano, feeling the ground rumble beneath your feet, watching as the mountain itself seems to come alive. Steam rises from vents in the rock, the air smells of sulfur, and if you're watching during an eruption, you might see glowing rivers of molten rock flowing down the mountainside, or towering columns of ash rising into the sky. Volcanoes are some of the most dramatic reminders that our planet is alive, constantly changing, with tremendous heat and energy churning beneath the surface. So get comfortable, relax, and let your imagination travel with us as we journey inside volcanoes, discovering their secrets and understanding these magnificent mountains that have shaped our planet for billions of years. What exactly is a volcano? At its simplest, a volcano is an opening in Earth's surface where molten rock, gases, and debris can escape from deep underground. Think of it like a safety valve on a pressure cooker. Deep inside Earth, temperatures are incredibly hot, hot enough to melt rock. This molten rock needs somewhere to go, and volcanoes provide that escape route. When we look at Earth from space, it seems solid and unchanging. But beneath the thin, rocky crust we live on, our planet is anything but solid. Just below the crust is a layer called the mantle, which extends about 2,900 kilometers down toward Earth's core. The mantle is so hot that rock there becomes soft and can flow very slowly, like extremely thick honey. Even deeper, at Earth's core, temperatures reach about 5,000 degrees Celsius, as hot as the surface of the sun. All this heat has to go somewhere. It creates convection currents in the mantle, where hot rock rises toward the surface while cooler rock sinks down. This constant circulation of rock, moving at about the same speed your fingernails grow, is what drives almost everything that happens on Earth's surface, from earthquakes to the formation of mountains to the creation of volcanoes. Earth's outer layer, the crust, isn't one continuous shell. It's broken into large pieces called tectonic plates. These plates fit together like a giant jigsaw puzzle, but unlike puzzle pieces, they're constantly moving, pushed and pulled by the flowing mantle beneath them. There are about 15 major tectonic plates and several smaller ones, all moving in different directions at different speeds. Most volcanoes form at the boundaries between these plates, where they interact in various ways. Understanding these boundaries is key to understanding why volcanoes exist and where they're located. The first type of boundary is called a divergent boundary, where two plates move apart from each other. As the plates separate, hot mantle rock rises up to fill the gap. The decrease in pressure causes this rock to melt, forming magma. The magma rises toward the surface and erupts, creating new crust. Most divergent boundaries are under the ocean, forming features called mid-ocean ridges. The mid-Atlantic ridge, which runs down the center of the Atlantic Ocean, is a perfect example. Iceland sits directly on this ridge, which is why it has so many volcanoes and hot springs. The second type is a convergent boundary, where two plates move toward each other. What happens here depends on what types of plates are colliding. When an oceanic plate meets a continental plate, the heavier oceanic plate gets pushed down beneath a lighter continental plate in a process called subduction. As the oceanic plate descends, it heats up. Water trapped in the rocks and sediments on the descending plate is released, and this water lowers the melting point of the surrounding mantle rock. The result is magma formation, and this magma rises through the overlying plate to form volcanoes. The volcanoes that form at these subduction zones are often the most explosive and dangerous. The Andes Mountains in South America, which contain many active volcanoes, formed this way when the oceanic Nazca Plate subducted beneath the South American plate. The Cascade Range in the northwestern United States, home to Mount St. Helens and Mount Rainier, formed where the Juan de Fuca plate subducts beneath the North American plate. When two oceanic plates converge and one subducts beneath the other, the result is a chain of volcanic islands called an island arc. Japan, the Philippines, and the Aleutian Islands of Alaska are all examples of island arcs formed this way. The third major way volcanoes form is over hotspots. A hotspot is a place where an unusually hot column of mantle rock, called a mantle plume, rises from deep inside Earth. The plume melts rock in the crust above it, creating magma that erupts at the surface. Unlike volcanoes at plate boundaries, hotspot volcanoes can form right in the middle of a tectonic plate. The Hawaiian Islands are the most famous example of hotspot volcanism. The Pacific plate is slowly moving northwest over the Hawaiian hotspot. As the plate moves, it carries old volcanoes away from the hotspot, and new volcanoes form in their place. This has created a chain of islands and underwater mountains stretching across thousands of kilometers of ocean. The Big Island of Hawaii, at the southeast end of the chain, is currently over the hotspot and has active volcanoes. The other islands, farther northwest, are older and no longer volcanically active. Now let's talk about magma and lava, because understanding these is crucial to understanding volcanoes. Magma is molten rock beneath Earth's surface. When magma erupts and flows onto the surface, we call it lava. The terms describe the same material, just in different locations. Not all magma is the same. Magma varies in its chemical composition, temperature, and gas content, and these differences determine how a volcano behaves when it erupts. The most important factor is silica content. Silica is a compound made of silicon and oxygen, and it's the main component of most rocks in Earth's crust. Basaltic magma has low silica content, typically around 50%. It's very hot, with temperatures between 1000 and 1200 degrees Celsius. Because it has relatively low viscosity, meaning it's quite runny, basaltic lava flows easily and can travel long distances before cooling and solidifying. Most of the volcanic rock on Earth is basalt. The ocean floor is made almost entirely of basaltic rock, and many volcanic islands like Hawaii are built from basaltic lava flows. Andesitic magma has intermediate silica content, around 60%, and cooler temperatures of about 800 to 1000 degrees Celsius. It's thicker and more viscous than basaltic magma, so it doesn't flow as easily. Andesite is named after the Andes Mountains, where this type of lava is common. Andesitic eruptions can be quite explosive because gases get trapped in the thicker lava. Rhyolitic magma has the highest silica content, around 70% or more, and the coolest temperatures, typically 700 to 850 degrees Celsius. It's extremely thick and viscous, more like toothpaste than a liquid. Rhyolitic lava barely flows at all. Instead, it tends to pile up around the volcanic vent, sometimes forming steep-sided domes. Because gases can't escape easily from this thick lava, rhyolitic eruptions are often the most explosive and violent. The temperature of lava affects its behavior too. Hotter lava is thinner and flows more easily. As lava cools, it becomes thicker and eventually stops flowing entirely as it solidifies into rock. The fastest lava flows ever recorded moved at speeds of about 60 kilometers per hour, but most lava flows move much more slowly, at walking pace or slower. Gas content is another crucial factor. Magma contains dissolved gases, primarily water vapor, carbon dioxide, and sulfur dioxide. When magma is deep underground, high pressure keeps these gases dissolved in the liquid rock, but as magma rises toward the surface, pressure decreases and the gases start to come out of solution, forming bubbles. It's like opening a bottle of soda. When the bottle is sealed, the carbon dioxide is dissolved in the liquid. Open the cap, pressure drops, and bubbles form. In runny basaltic lava, gas bubbles can escape relatively easily, so eruptions are usually gentle, with lava flowing or fountaining from the vent. But in thick, viscous lava, gas bubbles get trapped. Pressure builds up until the lava literally explodes, fragmenting into tiny pieces of rock ash and pumice that are hurled into the air. This is why silica-rich volcanoes tend to have more explosive eruptions. When lava erupts and flows across the surface, it creates different types of lava flows depending on its composition and how fast it's moving. Basaltic lava, which is runny and hot, often forms two distinctive types of flows. Pahoho lava has a smooth, ropey surface that forms when the top of the flow cools and solidifies while the liquid lava beneath continues to move. The solid crust wrinkles and folds, creating patterns that look like twisted rope. Pahoho is a Hawaiian word, and this type of lava is common on the Hawaiian Islands. You can actually walk on hardened pahoho, though you need to be careful because there might still be hot lava flowing beneath the surface. A lava is rougher and more jagged. It forms when lava flows more quickly or begins to cool and become more viscous. The surface breaks up into sharp clinker-like chunks. Walking on AA lava is difficult and can shred your shoes. AA is also a Hawaiian word, and legend says it's named for the sound people make when they walk barefoot on it. When basaltic lava erupts underwater, it forms pillow lava. The cold water causes the outer surface of the lava to cool almost instantly, forming a rounded pillow-like shape. More lava pushes out, forming another pillow, and gradually a pile of these pillows builds up. Pillow lava is common along mid-ocean ridges where underwater volcanoes are constantly erupting. Sometimes lava flows into tubes. When lava first erupts, the surface exposed to air cools and hardens, forming a crust. But underneath, lava continues to flow through this insulating tunnel. Lava tubes can extend for many kilometers, transporting lava far from the eruption site while keeping it hot and fluid. When the eruption stops and the lava drains out, it leaves behind an empty tube, a cave that people can explore. Some lava tubes in Hawaii are large enough to drive a car through. Volcanoes come in several distinct types, each with characteristic shapes and eruption styles. Understanding these types helps us predict how a volcano might behave. Shield volcanoes are the largest volcanoes on Earth. They have broad, gently sloping sides that resemble a warrior's shield lying on the ground, which is how they got their name. Shield volcanoes form from repeated eruptions of runny basaltic lava that flows long distances before solidifying. Each eruption adds a new layer, gradually building up the volcano. The Hawaiian Islands are classic shield volcanoes. Mauna Loa, on the Big Island of Hawaii, is the largest volcano on Earth by volume. From its base on the ocean floor to its summit, Mauna Loa rises about 10,000 meters, taller than Mount Everest. But because its slopes are so gentle, rising only a few degrees, it doesn't look nearly as dramatic as a pointy mountain. You can drive to the summit of Mauna Loa on a paved road. Shield volcanoes generally have relatively gentle eruptions. Lava flows from vents or fissures, sometimes creating spectacular lava fountains that shoot molten rock hundreds of meters into the air. But these eruptions rarely threaten people's lives because the lava flows slowly enough that people can evacuate. Composite volcanoes, also called stratovolcanoes, are the classic cone-shaped mountains most people picture when they think of volcanoes. They have steep sides and a pointed summit. Mount Fuji in Japan, Mount Rainier in Washington, and Mount Vesuvius in Italy are all composite volcanoes. Composite volcanoes form from a mixture of lava flows and explosive eruptions of ash and rock fragments called pyroclastic material. The name stratovolcano comes from the alternating layers, or strata, of lava and pyroclastic material that make up the volcano. These volcanoes typically form at subduction zones where the magma is more silica-rich, thicker, and more prone to explosive eruptions. Composite volcanoes are more dangerous than shield volcanoes because their eruptions are often violent and unpredictable. They can produce pyroclastic flows, which are avalanches of hot gas and rock that race down the mountainside at hundreds of kilometers per hour, destroying everything in their path. They can also produce lahars, which are mud flows created when volcanic material mixes with water from melted snow or ice on the volcano. Lahars can travel far from the volcano, burying valleys and towns under meters of mud. Cinder cones are the smallest and simplest type of volcano. They form when blobs of lava are thrown into the air during eruptions. The lava cools and hardens as it flies through the air, falling back to Earth as cinders or volcanic fragments. These pile up around the vent, forming a cone-shaped hill with steep sides and a bowl-shaped crater at the summit. Most cinder cones are only a few hundred meters tall. Cinder cones usually erupt only once. After the eruption, the volcano goes quiet forever. Many cinder cones form on the flanks of larger volcanoes, or in volcanic fields where there are many small cones scattered across the landscape. Paricutin in Mexico is a famous cinder cone because scientists watched it being born in 1943. It grew from a crack in a farmer's cornfield, eventually reaching 324 meters tall before the eruption ended 9 years later. Lava domes form when thick, viscous lava oozes out of a vent but is too sticky to flow away. Instead, it piles up over the vent, forming a steep-sided dome or bulge. The outside of the dome cools and hardens, but more lava continues to push up from beneath, causing the dome to grow. Sometimes the dome becomes unstable and collapses, producing dangerous pyroclastic flows. Lava domes often form inside the craters of larger volcanoes after an explosive eruption. Mount St. Helens, which erupted catastrophically in 1980, has been building a lava dome inside its crater for decades. The dome grows slowly, sometimes in sudden spurts that last only hours or days. Calderas are huge volcanic depressions that form when a magma chamber beneath a volcano empties during a massive eruption. Without the magma to support it, the ground above collapses, creating a giant crater that can be tens of kilometers across. Calderas are among the most dangerous volcanic features because they're associated with the most explosive eruptions imaginable. Crater Lake in Oregon sits in a caldera that formed about 7,700 years ago when Mount Mazama erupted and then collapsed. The eruption was so large that ash from it can be found across much of western North America. After the mountain collapsed, the caldera gradually filled with rain and snowmelt, creating the deep blue lake we see today. Yellowstone National Park sits on top of a giant caldera, one of the largest in the world. The Yellowstone supervolcano has erupted 3 times in the past 2 million years, with the last eruption occurring about 640,000 years ago. These eruptions were thousands of times more powerful than any volcanic eruption in recorded human history. Now let's journey beneath the ocean's surface and explore underwater volcanoes, because most of Earth's volcanic activity actually happens underwater, hidden from view. The mid-ocean ridge system is the longest mountain range on Earth, stretching about 65,000 kilometers around the globe like the seam on a baseball. This underwater mountain range marks divergent plate boundaries where tectonic plates are moving apart. As the plates separate, magma rises from the mantle and erupts, creating new ocean floor in a process called seafloor spreading. Volcanic eruptions happen constantly along the mid-ocean ridges, but we rarely notice because they're kilometers beneath the sea surface. These eruptions are usually gentle because the magma is basaltic and runny. The water pressure at these depths is enormous, hundreds of times greater than atmospheric pressure at sea level, and this pressure affects how the lava behaves. Instead of flowing freely, the lava forms those pillow-shaped blobs we mentioned earlier. The mid-ocean ridges are home to hydrothermal vents, some of the most extreme and fascinating environments on Earth. These vents form when seawater seeps down through cracks in the newly formed oceanic crust. As the water descends, it comes close to magma chambers beneath the ridge. The magma heats the water to temperatures of 300 to 400 degrees Celsius. Hot water, under the immense pressure of the deep ocean, doesn't boil. Instead, it becomes a powerful solvent, dissolving minerals from the surrounding rock. This superheated, mineral-rich water then rises back up through the crust and erupts from vents on the seafloor, creating what look like underwater geysers. When the hot vent fluid mixes with the cold ocean water, The dissolved minerals precipitate out, forming clouds that make it look like the vents are smoking. Black smokers get their name from the dark clouds of iron sulfide and other minerals that pour from them. White smokers produce lighter-colored clouds from different minerals. Over time, the precipitated minerals build up around the vent, forming chimney-like structures that can grow several meters tall. These chimneys are fragile and can collapse, but new ones form constantly. The area around hydrothermal vents is one of the few places on Earth where life doesn't depend on sunlight. Instead, microbes use the chemicals in the vent fluid as an energy source through a process called chemosynthesis. These microbes form the base of a unique food chain that includes giant tube worms over 2 meters long, white crabs, blind shrimp, and many other creatures found nowhere else on Earth. Submarine volcanoes, also called seamounts, are mountains on the ocean floor that don't reach the surface. There are tens of thousands of seamounts in the world's oceans, and many of them are volcanic. Some seamounts are isolated, while others form chains. The Hawaiian Emperor Seamount chain extends northwest from Hawaii for over 5,000 kilometers, representing the track of the Hawaiian hotspot as the Pacific plate has moved over it for the past 70 million years. When a submarine volcano grows tall enough to break the surface, it becomes a volcanic island. This is how all volcanic islands are born, rising from the deep ocean as accumulated lava builds the mountain higher and higher. The process can take hundreds of thousands or even millions of years. The youngest Hawaiian island, the Big Island, is still growing as lava continues to erupt from Kilauea and other volcanoes. There's actually a new Hawaiian island currently forming underwater. It's called Loihi, and it sits on the ocean floor southeast of the Big Island, directly over the hotspot. Loihi is still about 1,000 meters below sea level, but it's actively erupting, and in perhaps tens of thousands of years, it will emerge above the waves to become Hawaii's newest island. Some of the most explosive volcanic eruptions in history have involved the interaction of magma with water. When magma rises into an aquifer or a lake, or when a volcanic island erupts, the water can flash instantly to steam, creating massive explosions. These are called phreatomagmatic eruptions, and they can be incredibly violent, even with relatively small amounts of magma. Surtsey, a small island off the coast of Iceland, was born in 1963 when an underwater eruption broke the surface. For several years, explosive eruptions built the island higher. Once the volcanic cone rose high enough that seawater could no longer enter the vent, the eruptions became less explosive, and lava flows added more land. Today, Surtsey is a protected natural laboratory, where scientists study how life colonizes new volcanic islands. Let's now explore one of the most famous features on Earth, the Ring of Fire. This is a horseshoe-shaped belt of volcanic and seismic activity that nearly encircles the Pacific Ocean. It's called a ring, though it's really more of a horseshoe or arc. The Ring of Fire is about 40,000 kilometers long and up to 500 kilometers wide. The Ring of Fire contains about 75% of the world's active and dormant volcanoes, over 450 in total. Some estimates go as high as 750 or more, depending on how you count smaller volcanic features. Approximately 90% of the world's earthquakes occur in the Ring of Fire, including most of the largest and most destructive quakes in history. The Ring of Fire exists because the Pacific Plate and several smaller plates around its edges are all converging with the surrounding plates. Around nearly the entire Pacific Ocean, oceanic plates are subducting beneath continental or other oceanic plates. This creates the volcanic arcs and chains that mark the Ring of Fire. Starting in South America, the Ring of Fire runs along the Andes Mountains, where the Nazca and Antarctic plates subduct beneath the South American plate. This section includes many active volcanoes in Chile, Argentina, Bolivia, Peru, Ecuador, and Colombia. Moving north, the ring continues along Central America and Mexico, where the Cocos Plate subducts beneath the Caribbean and North American plates. Volcanoes here include those in Costa Rica, Nicaragua, Guatemala, and the famous volcanoes near Mexico City. The North American segment includes the volcanoes of the Cascade Range in the northwestern United States and southwestern Canada. Mount St. Helens, Mount Rainier, Mount Shasta, and Mount Hood are part of this chain. These form where the Juan de Fuca Plate subducts beneath the North American Plate. Continuing north and then west, the ring passes through Alaska and the Aleutian Islands, where the Pacific Plate subducts beneath the North American Plate. This region has dozens of active volcanoes, many on remote islands in the Aleutian chain. Curving south and west, the Ring of Fire continues through Russia's Kamchatka Peninsula, the Kuril Islands, Japan, the Philippines, Indonesia, Papua New Guinea, New Zealand, and many other island nations. Each of these regions marks a subduction zone, where one plate dives beneath another. Some of the world's most famous and destructive volcanoes are part of the Ring of Fire. Mount Fuji in Japan, a beautifully symmetrical composite volcano, is sacred in Japanese culture and has been climbed by pilgrims for centuries. While it hasn't erupted since 1707, it's considered active and could erupt again. Mount Pinatubo in the Philippines erupted in 1991 in one of the largest eruptions of the 20th century. The eruption ejected about 10 cubic kilometers of material and created an ash column 35 kilometers high. More than 800 people died, many from collapsing buildings weighed down by wet volcanic ash. The eruption cooled global temperatures by about half a degree Celsius for a year or two because of the sulfur dioxide released into the stratosphere. Indonesia has more volcanoes than any other country, with over 120 active volcanoes. Two of the deadliest eruptions in recorded history occurred there. Mount Tambora erupted in 1815 in the most powerful eruption in recorded history, killing at least 70,000 people directly and many more from the famine and disease that followed. The eruption released so much ash and sulfur dioxide into the atmosphere that it caused global cooling. The year 1816 became known as the year without a summer. Crops failed across Europe and North America, causing widespread hunger. Krakatoa, also in Indonesia, erupted catastrophically in 1883. The explosion was heard 3,000 miles away, one of the loudest sounds ever recorded. Tsunamis triggered by the eruption killed over 36,000 people. The eruption blew away most of the island, and the ash in the atmosphere created spectacular red sunsets around the world for years. Some art historians think the vivid red sky in Edvard Munch's famous painting The Scream was inspired by Krakatoa sunsets. The Ring of Fire is not just a geographic curiosity. It represents one of the most geologically active regions on Earth, where the forces that shape our planet are constantly at work. The same tectonic processes that create the Ring of Fire's volcanoes also cause its earthquakes, build mountain ranges, and create deep ocean trenches like the Mariana Trench, the deepest point in Earth's oceans. Living near Ring of Fire volcanoes comes with risks, but it also brings benefits. Volcanic soil is extremely fertile once it weathers, because volcanic ash and rock contain minerals that plants need. Some of the most productive agricultural regions on Earth are on volcanic slopes. The geothermal energy from volcanic regions provides electricity and heating for millions of people in countries like Iceland, New Zealand, and the Philippines. And volcanic landscapes attract tourists, supporting local economies. Scientists constantly monitor Ring of Fire volcanoes, measuring ground deformation, gas emissions, and earthquake activity to watch for signs of impending eruptions. This monitoring has improved dramatically in recent decades, helping to save countless lives by providing warning before major eruptions. Living near Ring of Fire volcanoes comes with risks, but it also brings benefits. Volcanic soil is extremely fertile once it weathers, because volcanic ash and rock contain minerals that plants need. Some of the most productive agricultural regions on Earth are on volcanic slopes. The geothermal energy from volcanic regions provides electricity and heating for millions of people in countries like Iceland, New Zealand, and the Philippines. and volcanic landscapes attract tourists, supporting local economies. Scientists constantly monitor Ring of Fire volcanoes, measuring ground deformation, gas emissions, and earthquake activity to watch for signs of impending eruptions. This monitoring has improved dramatically in recent decades, helping to save countless lives by providing warning before major eruptions. One of the most dangerous phenomena that volcanoes produce is called a pyroclastic flow. The name comes from Greek words meaning fire and broken pieces, and that describes exactly what these flows are: avalanches of hot rock fragments, volcanic ash, and superheated gas that race down a volcano's slopes at incredible speeds. Pyroclastic flows are the deadliest of all volcanic hazards. They form during explosive eruptions when an eruption column becomes too heavy and collapses, or when part of a lava dome breaks away and tumbles down the mountainside. The flows are a churning mixture of gas and solid particles, and this mixture behaves almost like a liquid, flowing along the ground and following valleys. The temperature inside a pyroclastic flow can reach 1000 degrees Celsius, hot enough to instantly incinerate anything in its path. The flows move with terrifying speed, typically traveling at 100 kilometers per hour, but sometimes reaching speeds up to 700 kilometers per hour. That's faster than a racing car, faster than a hurricane, faster than anything could possibly run or drive to escape. Because pyroclastic flows are denser than air, they hug the ground as they move. They're heavy enough that they can't be stopped by buildings or forests. Everything in their path is destroyed, flattened, burned, and buried. The flows can travel many kilometers from the volcano, and they don't even need a clear path. Small flows might follow valleys, but large ones can flow over ridges and hills. The French have a name for glowing pyroclastic flows that light up the night sky, nuit ardente, which means burning cloud. This term became famous after the eruption of Mount Pelée on the Caribbean island of Martinique in 1902. On May 8th that year, the volcano suddenly erupted and sent a pyroclastic flow racing down toward the town of Saint-Pierre. The flow reached the town in less than 2 minutes, moving at over 160 kilometers per hour. Saint-Pierre was the largest city on Martinique, home to about 30,000 people. The pyroclastic flow killed nearly everyone in the city almost instantly. The superheated gas seared their lungs, and the force of the flow knocked down buildings and ships in the harbor. Only 2 people in the main town survived: a prisoner who was protected in a partially underground jail cell with thick stone walls, and a shoemaker who lived on the edge of town. The disaster was one of the deadliest volcanic events of the 20th century. When a pyroclastic flow finally stops moving, it deposits a layer of volcanic material called tuff. If the deposit was very hot when it settled, the particles can weld together, forming a rock called welded tuff, or ignimbrite. Some of the world's most spectacular rock formations are ancient ignimbrites from massive eruptions millions of years ago. Volcanoes also produce pyroclastic surges, which are similar to pyroclastic flows but less dense. Surges are a turbulent cloud of ash and gas that can travel even faster than flows and can cross barriers that would stop a flow, like bodies of water or ridges. The surge from Mount Pelée actually traveled over water to sink ships in the harbor. Let's talk about the gases that volcanoes release, because they're just as important as the solid lava and ash, and they affect our planet in profound ways. When magma rises toward the surface, dissolved gases come out of solution and expand, sometimes explosively. These gases don't just disappear. They enter Earth's atmosphere, where they can have effects that last for years. Water vapor is by far the most abundant volcanic gas, making up between 60 and 95% of all gases released during eruptions. Every time a volcano erupts, it adds water to Earth's atmosphere and eventually to the oceans. Over Earth's long history, volcanic eruptions have been one of the main sources of water on our planet's surface. The oceans themselves came largely from volcanic outgassing over billions of years. Carbon dioxide is typically the second most abundant gas. Volcanoes release about 200 million tons of carbon dioxide into the atmosphere each year. That sounds like a lot, but it's actually tiny compared to the amount humans release by burning fossil fuels, which is about 100 times more. Still, volcanic carbon dioxide has played an important role in Earth's climate over geologic time. Sulfur dioxide is one of the most important gases for understanding how volcanoes affect climate and the environment. When sulfur dioxide reaches the upper atmosphere, it reacts with water vapor to form tiny droplets of sulfuric acid. These droplets reflect sunlight back into space, cooling Earth's surface. Large volcanic eruptions that inject massive amounts of sulfur dioxide into the stratosphere can cool the entire planet for years. We've already mentioned Tambora in 1815, which caused the year without a summer. Mount Pinatubo's eruption in 1991 cooled global temperatures by about 0.5 degrees Celsius for the next couple of years. Scientists could measure this cooling with satellites and weather stations around the world. The sulfuric acid droplets eventually fall back to Earth as acid rain, which can damage forests, crops, and buildings. Acid rain from volcanoes can affect areas thousands of kilometers from the eruption site. In Iceland, when volcanoes erupt, farmers sometimes have to keep their sheep indoors because fluorine gas from the volcano can poison the grass the animals eat. Hydrogen sulfide is another sulfur gas that smells like rotten eggs. In low concentrations, it's just unpleasant, but in higher concentrations, it's toxic. Areas around active volcanoes often have this distinctive smell from hydrogen sulfide in the volcanic gases. Hydrogen chloride and hydrogen fluoride are acids that can be very dangerous. They irritate the skin, eyes, nose, throat, and lungs. In high enough concentrations, they can be lethal. These gases are heavier than air, so they can accumulate in low-lying areas, creating invisible death traps. Carbon dioxide is another gas that, while not toxic in low concentrations, can be deadly because it's heavier than air. In certain locations, carbon dioxide seeps out of the ground from underground volcanic sources and pools in low areas. Lake Nyos in Cameroon, Africa, sits in an old volcanic crater, and carbon dioxide from magma below seeps into the lake water. In 1986, the lake suddenly released a massive cloud of carbon dioxide that flowed down the valleys, displacing the air. The carbon dioxide suffocated 1,700 people and thousands of animals. Scientists now have a system that slowly releases the gas from the lake to prevent another disaster. Volcanic gases also contain trace amounts of mercury, radon, and even organic compounds. Scientists study these gases carefully because changes in the type or amount of gas a volcano releases can signal that an eruption is coming. One of the most famous volcanic eruptions in history destroyed the Roman cities of Pompeii and Herculaneum in the year 79 AD. This eruption of Mount Vesuvius has taught us an enormous amount about how explosive eruptions happen and how pyroclastic flows destroy. Mount Vesuvius is a composite volcano near the Bay of Naples in Italy. In Roman times, people didn't know it was a volcano. It had been quiet for hundreds of years, and its slopes were covered with vineyards and farms. The wealthy city of Pompeii, with about 20,000 residents, sat just a few kilometers from the mountain. On August 24th, in the early afternoon, Vesuvius suddenly erupted. We know the details because a 17-year-old boy named Pliny the Younger was staying with his uncle in a town across the bay. He watched the eruption and wrote 2 letters describing it years later. These letters are the oldest detailed eyewitness account of a volcanic eruption we have. Pliny described how a huge column of ash and pumice shot up from the volcano, rising 33 kilometers into the sky. The column looked like a pine tree, with a narrow trunk and a spreading top. Today, this type of eruption is called a Plinian eruption in his honor. The eruption column was so high that it penetrated into the stratosphere. Volcanic debris began raining down on Pompeii within an hour of the eruption's start. Pumice stones, light pieces of volcanic rock full of gas bubbles, fell from the sky like hail. At first they were small, but they got larger and larger. The pumice accumulated rapidly, covering roofs and streets. Some buildings collapsed under the weight. The eruption continued through the night. Many people in Pompeii decided to flee, but others stayed, seeking shelter in their homes or in sturdy public buildings. They thought the worst had passed. They were wrong. The following morning, August 25th, the eruption column became unstable and collapsed. Pyroclastic flows began racing down the mountain toward Pompeii. These flows moved at about 100 miles per hour and had temperatures of several hundred degrees Celsius. The first pyroclastic surge hit Pompeii around 7 in the morning. The superheated gas and ash killed anyone still alive in the city almost instantly. The extreme heat caused people's muscles to contract violently, freezing them in their final positions. More pyroclastic flows followed, burying the city under several meters of volcanic material. In total, the eruption released 100,000 times the thermal energy of the atomic bomb dropped on Hiroshima. It ejected about 4 cubic kilometers of material. At least 16,000 people died, though the exact number will never be known. Pompeii and Herculaneum were completely buried and forgotten for over 1,600 years. When archaeologists began excavating Pompeii in the 18th century, they found a city frozen in time. Buildings, streets, artwork, graffiti, even loaves of bread in bakeries were preserved under the ash. Most hauntingly, they found hollows in the ash where bodies had decayed. By filling these hollows with plaster, they created casts showing people in their final moments, some huddled together, some trying to protect their faces, some still holding their possessions. The eruption of Vesuvius gave scientists their first detailed look at how explosive eruptions work. The pattern Pliny described, of a high eruption column followed by collapse and pyroclastic flows, is now recognized at volcanoes around the world. Mount Vesuvius is still considered one of the most dangerous volcanoes on Earth because about 3 million people live near enough to be threatened if it erupts again, which it certainly will someday. Despite their dangers, volcanoes provide many benefits to people and to Earth itself. We've mentioned the fertile soil they create, but let's explore this more. When volcanic rock and ash weather and break down, they release minerals including potassium, phosphorus, calcium, magnesium, and iron. These are exactly the nutrients plants need to grow. The slopes of volcanoes in Indonesia, the Philippines, Japan, and Central America are among the most intensively farmed lands on Earth. Coffee, rice, vegetables, and tropical fruits thrive in volcanic soil. The island of Java in Indonesia has dozens of active volcanoes, and it's also one of the most densely populated places on Earth, partly because the volcanic soil is so productive. Even areas that were completely devastated by eruptions eventually recover and become green again. After Mount St. Helens erupted in 1980, scientists thought it would take centuries for life to return to the blast zone. Instead, within just a few years, plants began growing again. Now, decades later, forests are regrowing, and the area is full of wildlife. Nature is remarkably resilient. Volcanoes create new land, especially in the ocean. Every volcanic island started as an underwater eruption that eventually built a mountain high enough to break the surface. The newest Hawaiian island, Loihi, is currently under construction on the ocean floor. The island of Surtsey off Iceland appeared in 1963 and has been growing ever since. Volcanic islands provide habitats for unique plants and animals and stepping stones for species to spread across oceans. Geothermal energy from volcanic regions is a clean, renewable energy source. In Iceland, geothermal power provides heat and electricity for most of the population. Water is pumped down through hot rock near magma chambers. The rock heats the water, and the resulting steam drives turbines to generate electricity or is piped directly into buildings for heating. New Zealand, the Philippines, Kenya, and Italy also generate significant electricity from geothermal sources. Volcanoes have played a crucial role in making Earth habitable. The atmosphere we breathe came from volcanic outgassing over billions of years. Early Earth had almost no atmosphere, but as the planet cooled and its interior differentiated into core, mantle, and crust, volcanoes released the gases that would become our air and oceans. The carbon dioxide, nitrogen, and water vapor from volcanoes created an atmosphere that could trap heat and support the development of life. Even today, volcanoes help regulate Earth's climate over long time scales. They're part of a cycle that moves carbon between Earth's interior, the oceans, and the atmosphere. When oceanic crust subducts, it carries carbon-rich sediments down into the mantle. Some of that carbon eventually returns to the surface through volcanic eruptions. This cycle helps keep Earth's temperature relatively stable over millions of years. Volcanic hot springs and geysers are another benefit. These features, common in volcanic areas, provide habitat for unusual organisms, including bacteria that live at extreme temperatures. Scientists study these extremophiles to understand the limits of life and to find enzymes useful in medicine and industry. Hot springs also provide recreation and tourism. Yellowstone National Park, sitting on a supervolcano, attracts millions of visitors each year who come to see Old Faithful and other geothermal features. Volcanoes even create precious minerals and gemstones. Diamonds form deep in Earth's mantle and are brought to the surface rapidly by volcanic eruptions called kimberlite pipes. Without these volcanic pipes, we'd never find diamonds at the surface. Sulfur deposits around volcanic vents are mined for industrial use. Gold, silver, copper, and other metals often concentrate in hydrothermal systems around volcanoes, and many of the world's richest ore deposits formed this way. Scientists have learned to watch volcanoes carefully for signs of impending eruptions, and this monitoring saves lives. When magma rises beneath a volcano, it causes changes that we can measure. The ground swells and deforms as magma pushes up from below. Networks of GPS receivers and tilt meters can detect changes in the volcano's shape, sometimes measuring movements of just a few millimeters. Rising magma also breaks rock as it forces its way upward, causing earthquakes. Seismometers placed on and around volcanoes record these earthquakes. As an eruption approaches, earthquakes typically become more frequent and start to occur at shallower depths as the magma rises. Volcanologists can track the magma's movement by analyzing the pattern of earthquakes. The composition and quantity of gases released by a volcano also change before eruptions. As magma gets closer to the surface, more gas escapes. The ratio of different gases can indicate how close magma is to erupting. Scientists measure volcanic gases using instruments on the ground and in aircraft, and even from satellites in space. Satellites are powerful tools for monitoring volcanoes. They can measure ground deformation using radar, detect temperature changes, track volcanic plumes, and even measure how much sulfur dioxide is being released. This is especially useful for remote volcanoes that are difficult or dangerous to reach on the ground. All this data goes into volcano observatories, where scientists analyze it constantly. When signs indicate an eruption might be imminent, authorities can evacuate people from dangerous areas. This monitoring successfully predicted the eruption of Mount Pinatubo in 1991, allowing the evacuation of tens of thousands of people and saving countless lives. It's also helped with eruptions in Japan, Indonesia, Mexico, and many other countries. However, prediction isn't perfect. Some volcanoes erupt with little warning. Others show signs of unrest for weeks or years without erupting. False alarms cause economic disruption and can make people less likely to evacuate for real threats. Despite decades of research, volcanology is still as much art as science, requiring experienced judgment and an understanding of each individual volcano's personality. Different volcanoes have different eruption patterns and warning signs. Hawaiian shield volcanoes typically give plenty of warning, with days or weeks of increasing earthquakes before lava starts flowing. Explosive volcanoes at subduction zones can be more unpredictable. Some wake up with only hours or days of warning. Understanding each volcano's history and behavior is crucial for accurate forecasting. The Volcanic Explosivity Index, or VEI, is a scale scientists use to measure how powerful eruptions are. It goes from 0 to 8, with each number representing eruptions 10 times more powerful than the previous number. The scale is logarithmic, like the Richter scale for earthquakes. A V0 eruption is non-explosive, just lava quietly flowing from a vent. Hawaiian eruptions typically rate 0 or 1. A V1 eruption produces at least 10,000 cubic meters of ejected material. V2 eruptions, like those that happen regularly in Japan and Indonesia, produce at least 1 million cubic meters. The eruption of Mount St. Helens in 1980 was a V5, ejecting 1 cubic kilometer of material. The Vesuvius eruption that destroyed Pompeii was also V5. Pinatubo in 1991 was V6, releasing about 10 cubic kilometers of material. VI7 eruptions are extremely rare and catastrophic. Tambora in 1815 was V7, ejecting 100 cubic kilometers of material. These eruptions are called supercolossal. Only 7 V7 eruptions have occurred in the past 10,000 years. V8 eruptions are called megacolossal and are even rarer. They eject more than 1,000 cubic kilometers of material. The most recent V8 eruption was Taupo in New Zealand about 26,000 years ago. The Yellowstone supervolcano has had 3 V8 eruptions in its history, the most recent 640,000 years ago. Such eruptions can affect the entire planet, dropping global temperatures, disrupting weather patterns, and potentially threatening civilization itself. Scientists worry about what would happen if a supervolcano like Yellowstone or Toba in Indonesia erupted today. The immediate area would be completely devastated. Volcanic ash would cover huge portions of continents, making them uninhabitable and destroying crops. The sulfur dioxide injected into the stratosphere would cool the planet, potentially causing crop failures worldwide. Recovery would take years or decades. Fortunately, supervolcano eruptions are extremely rare. The chances of one occurring in any given human lifetime are very small. Volcanoes have shaped human history in many ways. Besides the obvious disasters like Vesuvius and Tambora, volcanic eruptions have toppled civilizations, inspired myths and religions, created legends, and influenced art and literature. The explosion of Thera, a volcano in the Aegean Sea, around 1600 BC, was one of the largest eruptions of the past 10,000 years. It destroyed the Minoan civilization on the island and may have inspired the legend of Atlantis. Volcanoes appear in the mythologies of cultures around the world. The ancient Greeks believed that Hephaestus, the god of fire and metalworking, had his forge beneath volcanoes. Polynesians saw volcanic eruptions as manifestations of Pele, the goddess of fire. Indigenous people near Mount Shasta in California considered it a sacred mountain where the spirit world touched the physical world. As you relax and let your mind wander through this volcanic landscape, imagine the incredible forces at work deep beneath Earth's surface, the heat and pressure that melts rock, the slow movement of tectonic plates, the magma rising toward the surface. Picture a shield volcano in Hawaii with lava flowing peacefully to the sea, or a composite volcano in the Andes with snow on its summit hiding the molten rock beneath. Think about how volcanoes have created the very ground we walk on, shaped our planet's surface, filled our oceans, and made our atmosphere. They're reminders that Earth is alive, constantly changing, with forces we're only beginning to understand. Imagine the incredible forces at work deep beneath Earth's surface, the heat and pressure that melts rock, the slow movement of tectonic plates, the magma rising toward the surface. Picture a shield volcano in Hawaii with lava flowing peacefully to the sea, or a composite volcano in the Andes with snow on its summit hiding the molten rock beneath. One of the most spectacular and mysterious phenomena volcanoes produce is volcanic lightning. When large explosive eruptions send towering columns of ash into the sky, electric bolts often flash within the dark clouds, creating what scientists call dirty thunderstorms. The first person to describe volcanic lightning in writing was Pliny the Younger, watching Vesuvius erupt in 79 AD. He wrote about intense darkness, punctuated by fitful gleams of torches obscured by the transient blaze of lightning. Volcanic lightning forms differently than ordinary lightning in thunderstorms. In regular thunderstorms, lightning happens when ice crystals collide inside clouds, knocking electrons off and building up electrical charges. Eventually, the difference in charge becomes so great that electricity jumps between the cloud and the ground, or between different parts of the cloud, creating the flash we see as lightning. But volcanic lightning can occur even without ice crystals. The main mechanism is called triboelectric charging, which is simply the fancy scientific name for static electricity created by friction. When volcanic ash particles shoot out of the volcano at high speed, they crash into each other millions and millions of times. Each collision can knock electrons off one particle and onto another. Some particles become positively charged, others negatively charged. Near the vent, where the eruption is most intense and ash is densest, these collisions happen constantly. The ash cloud quickly builds up enormous electrical charges. When the difference in charge becomes too great, electricity suddenly jumps through the cloud, creating a brilliant flash of lightning right within the volcanic plume. Higher up in the atmosphere, volcanic plumes can also produce lightning through the same ice crystal mechanism as thunderstorms. As the eruption column rises, it carries water vapor from the magma and from any bodies of water the eruption has vaporized. When this moist ash cloud reaches high, cold altitudes, ice crystals form. These crystals collide just like in a thunderstorm, generating additional lightning in the upper parts of the plume. This means volcanic eruptions can create two types of lightning at once: near-vent lightning from ash collisions close to the volcano, and ice-generated lightning higher up in the stratosphere. Photographers have captured images showing hundreds of lightning bolts branching through volcanic plumes, creating scenes that look almost supernatural. Scientists have observed volcanic lightning at eruptions around the world: Alaska's Mount Augustine, Iceland's geological, Sicily's Mount Etna, the Philippines' Taal volcano, and Guatemala's Volcán de Fuego have all produced spectacular lightning displays. Generally, the more ash an eruption produces, and the higher the eruption column rises, the more intense the lightning will be. Eruption columns that reach above 7 kilometers in height are much more likely to generate lightning than shorter plumes. The lightning itself isn't just beautiful, it's dangerous. Each bolt carries tremendous electrical current and can heat the air around it to 30,000 degrees Celsius, 5 times hotter than the surface of the sun. The rapid heating causes the air to explode outward, creating thunder. During a large eruption, the combination of the roar of the volcano, the boom of thunder, and the crack of lightning creates a sound unlike anything else in nature. Now let's explore one of the most mesmerizing volcanic features: lava lakes. A lava lake is exactly what it sounds like: a lake of molten lava sitting in a volcanic crater or vent. Unlike the lava that erupts and then cools and solidifies, lava in these lakes stays molten for months, years, or even decades, constantly churning and glowing. Only a handful of lava lakes exist in the world at any given time, and they're found at some of the most remote and dangerous volcanoes. The largest lava lake on Earth is at Mount Nyiragongo in the Democratic Republic of Congo, near the border with Rwanda. This active volcano sits at an elevation of about 3,400 meters in the Virunga Mountains. Nyiragongo's crater is about 1.2 kilometers wide, and the lava lake within can reach depths of several hundred meters. The lava here is exceptionally fluid, more liquid than lava at almost any other volcano. This extreme fluidity is both beautiful and dangerous. When Nyiragongo has erupted, lava has drained from the lake and flowed down the mountainside at speeds up to 60 kilometers per hour, faster than any person could run. In January 1977, the walls of Nyiragongo's lava lake fractured, and lava drained out catastrophically. Lava rivers raced down the mountain, reaching the nearby city of Goma in less than an hour. At least 70 people died, and thousands of people's homes were destroyed. Another major eruption occurred in 2002, when lava flows reached Goma again, destroying about 15% of the city and forcing hundreds of thousands of people to evacuate. Despite these dangers, Nyiragongo's lava lake continues to bubble and churn, a window into the molten interior of our planet. Erupted in Ethiopia hosts another famous lava lake, actually two of them. The volcano's name translates to smoking mountain, and it sits in the Afar Depression, one of the hottest and most inhospitable places on Earth. The Afar Depression is a desert badlands where three tectonic plates are pulling apart, slowly splitting Africa. Erupted's lava lake has existed continuously since at least 1906, making it possibly the longest-lived lava lake on Earth. The lake sits at the bottom of a pit crater at the Volcanoes summit. Scientists and adventurous tourists can peer over the crater rim and watch the lava churning below, though they must be careful. The fumes are toxic, the heat is intense, and the volcano can erupt with little warning. In 2017, an eruption killed several people who were camping near the crater. Mount Erebus in Antarctica has the southernmost active lava lake in the world. This volcano sits on Ross Island, the same island where many Antarctic research stations are located. Erebus is unique among lava lakes because it exists in one of the coldest environments on Earth. The contrast between the molten lava, at over 1,000 degrees Celsius, and the Antarctic air, which can be minus 40 degrees or colder, creates dramatic temperature gradients. Erebus's lava is phonolite, a rare type of magma that's more viscous than basalt, but more fluid than rhyolite. The lake frequently produces strombolian eruptions, hurling volcanic bombs out of the crater. These bombs, some the size of cars, fly through the frigid air and land on the snow-covered slopes around the summit. Scientists have studied Erebus extensively because it's relatively accessible and because its lava lake provides insights into how magma behaves. Hawaii's Kilauea volcano has had persistent lava lakes in two locations, Halemaumau crater at the summit and Pu'u'o on the volcano's flank. These lakes existed for years, allowing scientists to monitor them closely and tourists to view them from safe observation areas. In 2018, however, a major eruption and collapse event caused both lakes to drain and disappear. Whether they'll reform remains to be seen. Masaya volcano in Nicaragua has a lava lake in its Santiago crater. This lake appears and disappears depending on the volcano's activity level. When active, the glowing lake attracts scientists and thrill-seekers from around the world. The Spanish conquistadors who first encountered Masaya in the 16th century thought the lava lake was a mouth of hell and performed exorcisms to try to close it. Vanuatu's Ambrim volcano has lava lakes in two craters named Benbow and Marum. The Marum crater's lava lake was even mapped by Google Street View, making it possible for anyone with an internet connection to virtually stand on the crater rim and look down at boiling lava hundreds of meters below. Lava lakes form where magma from deep underground can reach the surface relatively easily, creating a sustained connection between the subsurface magma chamber and the surface. The lava continuously circulates, with hot fresh magma rising from depth while cool surface lava sinks back down. This convection keeps the lake molten. The surface of a lava lake is endlessly fascinating to watch. It's not smooth but broken into plates that jostle against each other like broken ice on a frozen lake, except these plates are red-hot rock. Between the plates, brilliant orange cracks reveal the even hotter lava below. The plates slowly move as the lava circulates, and occasionally bubbles of gas burst through, sending globs of lava into the air. When volcanoes erupt explosively, they throw out fragments of molten rock called volcanic bombs or lava bombs. These are larger than 64 millimeters in diameter, distinguishing them from smaller fragments like ash and lapilli. Some volcanic bombs are truly enormous. The 1935 eruption of Mount Asama in Japan threw bombs 5 to 6 meters across, the size of a small house, and hurled them 600 meters from the vent. Volcanic bombs are incredibly dangerous. They're not just heavy rocks, they're flying projectiles that can weigh tons and travel at high speeds. They can crash through roofs, destroy vehicles, and kill anyone they hit. In 1993, 6 scientists near the summit of Galeras volcano in Colombia were killed by volcanic bombs when the volcano erupted unexpectedly during a research visit. In 2018, a basketball-sized bomb from Kilauea crashed through the roof of a tour boat, injuring 23 people. Most volcanic bombs solidify during flight as they cool in the air, but some are still partially molten when they land. The shapes of bombs tell us about the magma they came from. Bombs are classified by their shapes, and each shape has a name that often describes exactly what it looks like. Spindle bombs or fusiform bombs are almond-shaped or football-shaped. They form when a blob of very fluid lava is thrown into the air. As it spins during flight, surface tension and aerodynamic forces pull it into a streamlined shape. These bombs often have smooth surfaces with lines showing the direction of airflow around them as they flew. Ribbon bombs form when lava is ejected as elongated strings or ribbons. The ribbons may break apart during flight or upon impact with the ground, leaving long curved pieces that really do look like stone ribbons. These form from highly fluid basaltic magma. Bread crust bombs have a distinctive fractured surface that looks like the crust of a loaf of bread. These form when the outside of a bomb cools and hardens quickly, forming a solid crust, but the inside stays molten. Gas bubbles trapped inside continue expanding, causing the solid crust to crack and create the bread crust texture. These bombs are dangerous because they can explode from internal pressure as they cool. Cow dung bombs, despite their unappetizing name, are simply very fluid bombs that splash and flatten when they hit the ground, like a cow pat. They indicate extremely fluid lava, usually basaltic. Spherical bombs form when surface tension pulls blobs of molten lava into perfect spheres during flight. These look like giant ball bearings made of rock. Cord bombs have a solid rock fragment at their center, with solidified lava wrapped around it. The core might be a piece of older solidified magma from the volcano, or it might be a xenolith, a chunk of rock from Earth's crust or mantle that the magma picked up on its way to the surface. All these bombs, along with smaller fragments, collectively make up what volcanologists call tephra. This term, from a Greek word meaning ash, refers to all the solid material a volcano ejects into the air during explosive eruptions. Tephra is classified by size. The smallest particles, less than 2 millimeters across, are called ash. Despite the name, volcanic ash isn't ash in the same sense as what's left after burning wood. It's tiny fragments of volcanic glass and rock, with sharp edges that can damage engines, scratch surfaces, and injure lungs if inhaled. Lapilli are intermediate-sized fragments, between 2 and 64 millimeters, roughly from the size of a grain of rice to the size of a walnut. The name means little stones in Italian. Lapilli rain down during eruptions and can accumulate meters deep around a volcano. Anything larger than 64 millimeters is classified either as a block if it's angular, indicating it was solid when erupted, or a bomb if it's rounded or shows evidence of being molten during flight. Blocks are typically fragments of the volcano's walls or dome that were blasted out by the explosion. Bombs are pieces of magma. When tephra falls back to Earth and accumulates, it forms layers that geologists can study to understand a volcano's history. Each eruption creates its own layer, and by examining these layers, scientists can determine when past eruptions occurred, how powerful they were, and what type of magma was involved. This field of study is called tephrochronology, using tephra layers like pages in a history book. Tephra layers can be found hundreds or even thousands of kilometers from their source volcano. The largest explosive eruptions eject so much ash that it circles the globe. Thin layers of ash from huge eruptions have been found in ice cores from Greenland and Antarctica, in deep-sea sediment cores from the ocean floor, and in soil profiles on continents far from any volcano. These ash layers are incredibly useful to scientists beyond just volcanologists. Because a volcanic eruption happens in an instant, geologically speaking, ash layers provide time markers that can be used to date other geological and archaeological deposits. If you find the same distinctive ash layer in two different locations, you know both locations represent the same point in time. Some volcanoes produce something even more dangerous than bombs, volcanic or pyroclastic surges and flows that we discussed earlier. But there are additional hazards worth understanding. Lahars, or volcanic mud flows, occur when volcanic material mixes with water. The water can come from several sources: melted snow and ice on the volcano's summit, heavy rainfall during or after an eruption, water from a crater lake, or even from a river. Lahars behave like wet concrete or thick mud flowing down valleys at speeds up to 100 kilometers per hour. They can travel tens of kilometers from the volcano, following river valleys and burying everything in their path under meters of mud and rock. A lahar doesn't need an active eruption to occur. Heavy rains weeks or months after an eruption can remobilize loose volcanic debris and create lahars. The eruption of Nevado del Ruiz in Colombia in 1985 produced lahars that killed more than 23,000 people. The volcano's eruption was relatively small, but it melted ice and snow on the summit. This water mixed with volcanic ash and debris, creating enormous lahars that race down valleys. The town of Armero, located in a valley 48 kilometers from the volcano, was buried under 5 meters of mud. Most residents were asleep when the lahar arrived and had no warning. Volcanic gases can also create deadly hazards even without an eruption. We mentioned Lake Nyos earlier, where carbon dioxide from volcanic sources dissolved in the lake water. In certain conditions, lakes like this can overturn, suddenly releasing dissolved gas in a phenomenon called a limnic eruption. The gas, heavier than air, flows down valleys like an invisible river, displacing oxygen and suffocating any animals or people in its path. Volcanic ash is a severe hazard to aviation. Jet engines work by compressing air, mixing it with fuel, and igniting it. The hot exhaust gases then spin turbines that power the plane. But volcanic ash particles, when sucked into a jet engine, melt in the intense heat and then resolidify on the cooler turbine blades, coating them with a layer of glass. This can cause engines to fail in flight. Several planes have nearly crashed after flying through volcanic ash clouds. In 1982, a British Airways flight from Kuala Lumpur to Australia flew through an ash cloud from Indonesia's Mount Galunggung. All 4 engines failed, and the plane fell from over 11,000 meters to less than 4,000 meters before the crew managed to restart the engines and make an emergency landing. The passengers had no idea how close they came to disaster. Since then, volcanic ash advisory centers have been established around the world to track ash clouds and warn aviation authorities. When Iceland's geological erupted in 2010, ash clouds closed airspace over much of Europe for several days, stranding millions of passengers and costing airlines billions of dollars. Better safe than sorry when it comes to volcanic ash and flying. Volcanic ash can cause other problems too. It's heavy when wet, causing roofs to collapse. It's abrasive, damaging machinery and vehicles. It contaminates water supplies. It ruins crops. It coats solar panels, reducing their efficiency. It clogs filters and air conditioning systems. Fine ash can be carried by wind for weeks, affecting areas far from the eruption. The 1980 eruption of Mount St. Helens spread measurable ash across the United States, and people as far away as Oklahoma and Kansas were cleaning ash off their cars. But volcanoes don't just destroy, they also create. Some of the world's most beautiful and unique landscapes are volcanic. Volcanic mountains like Mount Fuji, Mount Kilimanjaro, and Mount Rainier are iconic landmarks. Volcanic islands like the Galapagos, Hawaii, and Iceland offer unique ecosystems found nowhere else. Volcanic rock formations can be spectacular. Devil's Tower in Wyoming is a volcanic plug, the solidified magma that cooled inside a volcanic vent after the rest of the volcano eroded away. It rises over 380 meters above the surrounding landscape, a striking column of rock visible for miles. Climbers from around the world come to scale its steep sides. The Giant's Causeway in Northern Ireland consists of about 40,000 interlocking basalt columns formed when lava flows cooled and contracted, naturally creating hexagonal pillars that look almost artificial. Local legend says the causeway was built by a giant as stepping stones to Scotland. The real explanation, cooling and cracking of lava, is almost as amazing as the legend. Volcanic activity creates geothermal features like geysers, hot springs, fumaroles, and mud pots. Yellowstone National Park has more geothermal features than anywhere else on Earth, over 10,000 individual features. Old Faithful Geyser, which erupts approximately every 90 minutes, has become one of America's most famous natural wonders. Geysers form where groundwater comes into contact with hot rock near a magma chamber. The water heats up and tries to turn into steam, but the weight of water above it keeps it liquid. Pressure builds until suddenly the water flashes to steam and erupts through a surface vent, shooting boiling water and steam tens of meters into the air. After the eruption, water slowly seeps back into the underground chambers, and the cycle begins again. Hot springs form from a similar process but without the explosive release. Hot water simply flows continuously to the surface, creating pools of warm or hot water. Many hot springs host unique ecosystems of thermophilic or heat-loving organisms. Some of these bacteria and archaea can survive in water at 90 degrees Celsius or even hotter. Scientists study these organisms to understand the limits of life and have found enzymes from hot spring bacteria useful in DNA analysis and other applications. Fumaroles are vents that release volcanic gases, primarily steam, but also other gases depending on the volcano. The gases often contain sulfur compounds that give fumaroles their characteristic rotten egg smell and sometimes deposit yellow sulfur crystals around the vent. Solfataras are fumaroles that emit sulfurous gases. Mudpots form where hot acidic volcanic gases rise through shallow groundwater, creating a mixture of clay, water, and gas that bubbles like thick porridge. The acids break down rock into clay, and the gas bubbles burst through the surface, creating the characteristic gloop-gloop sound. Some mudpots are colorful, with bacteria giving them pink, orange, or green hues. All these geothermal features require heat from magma chambers relatively close to Earth's surface. They're evidence that a volcanic system is active, even if the volcano itself isn't currently erupting. Monitoring temperature changes in geothermal features can provide clues about what's happening deep underground. A sudden increase in temperature or gas output might signal that magma is moving closer to the surface. Volcanic soils and volcanic landscapes also provide important ecological benefits. After an eruption destroys an area, succession begins almost immediately. Pioneer species, plants and animals that can tolerate harsh conditions, move in first. Lichens and mosses colonize bare rock. Wind-blown seeds sprout in cracks and crevices. Birds visit and leave droppings that contain seeds and nutrients. Gradually, soil builds up. Dead plants decompose. More complex plants establish themselves. After years or decades, shrubs and trees return. Animals follow. Within a human lifetime, an area that was completely devastated can be teeming with life again. This process has been observed at Mount St. Helens, where the blast zone is now full of plants and animals, and at Krakatoa, where a new volcanic island called Anak Krakatau, child of Krakatoa, rose from the sea and has been colonized by hundreds of plant and animal species. Volcanic islands in particular are natural laboratories for studying how life spreads and evolves. When a new volcanic island appears, it starts completely sterile, devoid of life. Every living thing on that island must arrive from somewhere else. Observing which species arrive first, how they get there, and how ecosystems develop is fascinating for biologists. The Galapagos Islands, visited by Charles Darwin and crucial to his development of the theory of evolution, are volcanic islands that have been colonized by unique species found nowhere else on Earth. As you drift deeper into relaxation, think about how volcanoes are windows into Earth's interior, showing us processes that usually happen hidden kilometers beneath our feet. Every eruption is a reminder that our planet is alive, dynamic, constantly reshaping itself. The ground we stand on, the air we breathe, the water in our oceans, all have connections to volcanic processes stretching back billions of years to when Earth was young. Volcanoes have shaped not just the landscape, but the very conditions that make life possible. They'll continue to do so long after humans are gone, part of an endless cycle of creation and destruction that will persist as long as Earth's interior stays hot, as long as tectonic plates continue to move, as long as our planet remains the dynamic, living world it is today. As you drift deeper into relaxation, think about how volcanoes are windows into Earth's interior, showing us processes that usually happen hidden kilometers beneath our feet. Every eruption is a reminder that our planet is alive, dynamic, constantly reshaping itself. While we've discussed active volcanoes extensively, it's important to understand that not all volcanoes continue erupting forever. Volcanoes can become dormant or even extinct, and understanding the difference helps us assess volcanic risk around the world. An extinct volcano is one that scientists believe will never erupt again. It has been cut off from its magma supply, either because the tectonic conditions that created it have changed, or because the hotspot that fed it has moved elsewhere, or simply because the volcanic system has cooled and solidified completely. Extinct volcanoes typically haven't erupted for tens of thousands or even millions of years and show no signs of renewed activity. One of the world's most famous extinct volcanoes is actually not a single mountain, but a volcanic plug. Edinburgh Castle in Scotland sits atop the solidified magma from a volcano that went extinct over 340 million years ago. The volcano itself eroded away long ago, but the hardened magma in the central vent was more resistant to erosion and remains today as a steep rocky hill perfect for a fortress. The Shiprock in New Mexico is another spectacular volcanic plug, rising about 480 meters above the surrounding desert. It formed when magma solidified in the throat of a volcano. Over millions of years, the softer volcanic cone eroded away, leaving only the resistant plug standing like a solitary tower. To the Navajo people, it's a sacred place called Tisi, meaning rock with wings. Mount Kilimanjaro in Tanzania is the highest mountain in Africa, rising 5,895 meters above sea level. This massive stratovolcano is actually composed of three separate volcanic cones: Shira, Mawenzi, and Kibo. Shira, the oldest and westernmost peak, became extinct over 500,000 years ago. Its summit collapsed, creating the Shira Plateau that hikers cross on their way to the main peak. Mawenzi, the second highest peak, is also extinct. Kibo, the tallest peak and the true summit of Kilimanjaro, is classified not as extinct but as dormant. A dormant volcano is one that hasn't erupted recently but still has the potential to erupt again. The last major eruption from Kibo was 360,000 years ago, but there was minor activity as recently as 200,000 years ago. Climbers who reach Kilimanjaro's summit and then descend into the crater can visit the ash pit and smell sulfur gases still being released from fumaroles. This gas emission proves that magma still exists beneath the mountain, keeping it technically alive. Most volcanologists believe Kibo could erupt again someday, though there's no sign this will happen in the near future. The mountain is closely monitored, and climbers have nothing to fear. The distinction between dormant and extinct isn't always clear-cut. Some volcanoes considered extinct have surprised scientists by erupting after thousands of years of silence. Mount Chiton in Chile was thought to be dormant or possibly extinct before it erupted in 2008 after more than 9,000 years of quiet. This teaches volcanologists to be careful about declaring volcanoes extinct. Now let's venture beyond Earth and discover that volcanoes exist on other worlds in our solar system. The study of these extraterrestrial volcanoes helps us understand how volcanic processes work under different conditions and gives us insights into the geology of alien worlds. Mars is home to the largest volcano in the entire solar system, Olympus Mons. This colossal shield volcano rises about 21 kilometers above the surrounding plains, nearly 2.5 times the height of Mount Everest. Its base is roughly 600 kilometers across, about the same size as the state of Arizona. If you stood at the center of Olympus Mons, you couldn't see its edges because they'd be below the horizon. Olympus Mons formed in a very different way than volcanoes on Earth. Mars doesn't have plate tectonics. Its crust is a single solid shell that doesn't move. A hot spot in the Martian mantle sat beneath the same piece of crust for millions or billions of years, continually erupting and building the volcano higher and higher. On Earth, the Hawaiian hotspot creates a chain of volcanoes as the Pacific plate moves over it. But on Mars, the crust stayed still, allowing one enormous volcano to form instead of a chain of smaller ones. Scientists aren't certain whether Olympus Mons is truly extinct or just dormant. Mars has cooled significantly since its early history, and volcanic activity has declined. However, some evidence suggests Mars might still have occasional eruptions. Marsquakes detected by NASA's InSight lander and young-looking lava flows in some regions hint that Mars might not be completely geologically dead. Recent research suggests some lava flows on Mars might be only a few million years old, which is extremely young in geological terms. Venus has more volcanoes than any other planet in the solar system, with over 80,000 volcanic features identified. The planet's surface is 90% covered in basaltic lava, indicating that volcanism has played a dominant role in shaping Venus. For decades, scientists debated whether Venus's volcanoes are extinct or still active. In 2023, researchers analyzing old radar images from NASA's Magellan spacecraft made a breakthrough discovery. They found that a volcanic vent associated with Mons, Venus's tallest volcano, changed in size and shape over an 8-month period in 1991. This strongly suggests active volcanism on Venus. Further studies in 2024 identified additional areas where new lava flows may have formed. These discoveries indicate that Venus is indeed volcanically active today, even though its surface temperature of 470 degrees Celsius and crushing atmospheric pressure make it impossible to observe eruptions directly. Venus's lack of plate tectonics, like Mars, means its volcanoes form differently than Earth's. Scientists think Venus might experience periodic global resurfacing events where the entire planet's surface is replaced by massive volcanic eruptions over a relatively short geological time. The last such event may have occurred about 500 million years ago, which would explain why Venus has relatively few impact craters compared to other rocky planets. Jupiter's moon Io is the most volcanically active body in the solar system, more active even than Earth. Io has about 400 active volcanoes constantly erupting. Some of its volcanic plumes shoot material 300 kilometers above the surface, high enough to be seen by spacecraft passing nearby. Io's volcanism is powered by tidal heating. Jupiter's immense gravity and the gravitational pulls of Jupiter's other large moons cause Io's solid interior to flex and deform as it orbits. This constant kneading generates enormous heat through friction, melting rock inside Io and creating the magma that feeds its volcanoes. Io is constantly being turned inside out by volcanic activity, resurfacing itself so rapidly that no impact craters exist on its surface. Every crater that forms is quickly buried by new lava flows. The volcanoes on Io are strange compared to Earth's. Because Io has almost no atmosphere and very low gravity, lava behaves differently. Volcanic plumes can reach extraordinary heights, and lava flows can extend for hundreds of kilometers. The temperature of some lava on Io is much hotter than typical Earth lava, possibly exceeding 1500 degrees Celsius, suggesting magma compositions we don't see on our planet. Other moons in the outer solar system have cryovolcanoes, which erupt water, ammonia, or methane instead of molten rock. Saturn's moon Enceladus shoots plumes of water ice and vapor from cracks near its south pole. These plumes reach hundreds of kilometers into space and contain organic molecules. Scientists think a liquid water ocean exists beneath Enceladus's icy crust, and the plumes might be a form of cryovolcanic activity driven by tidal heating, similar to what powers Io's volcanoes. Neptune's moon Triton also shows evidence of cryovolcanic activity. Dark plumes observed by Voyager 2 in 1989 might be nitrogen geysers erupting through the icy surface. Even distant Pluto shows evidence of cryovolcanoes. Mountains made of water ice and regions that appear to have been resurfaced by flows of frozen nitrogen suggest that this tiny dwarf planet, despite being incredibly cold, has or recently had volcanic-like activity. Looking to Earth's future, volcanic activity will continue for hundreds of millions or even billions of years. As long as Earth's interior remains hot and tectonic plates continue moving, volcanoes will keep erupting. However, the pattern of volcanism will change over time as Earth's interior gradually cools. In the immediate future, over the next decades and centuries, we can expect volcanoes to continue behaving much as they do today. Scientists estimate that somewhere between 50 and 70 volcanoes erupt each year around the world. Most eruptions are small and affect only local areas. Major explosive eruptions like Pinatubo in 1991 happen every few decades. Super eruptions are far rarer, occurring on average every 50,000 to 100,000 years. Though the timing is highly unpredictable, climate change adds a new wrinkle to volcanic activity. As glaciers and ice sheets melt due to global warming, the weight pressing down on Earth's crust decreases. This reduction in pressure, called isostatic rebound, can affect magma generation deep underground. When ice melts, pressure on the mantle decreases, allowing more melting to occur and potentially increasing magma production. Iceland provides a natural laboratory for studying this effect. At the end of the last ice age about 11,000 years ago, the massive ice sheets covering Iceland melted rapidly. Volcanic activity increased dramatically in response, with eruption rates rising by 30 to 50 times normal levels. This enhanced volcanic activity continued for about 1,500 years. Today, Iceland's glaciers are melting rapidly due to climate change, and scientists are monitoring whether a similar increase in volcanism might occur. Computer models suggest that magma generation beneath Iceland might already be double what it would be without the melting glaciers. The big question is how long it will take for this extra magma to reach the surface and cause eruptions. Similar effects might occur in other glaciated volcanic regions like Alaska, the Andes, and the Cascade Range. A 2020 study identified about 245 volcanoes worldwide that are fully or partially covered by ice and might experience changes in activity as that ice melts. The future could see more frequent volcanic eruptions in these regions, though predicting exactly when and where remains difficult. Climate change might also affect volcanic hazards in another way. Warmer temperatures lead to more intense precipitation in many regions. When heavy rains fall on loose volcanic deposits, they can trigger lahars even decades after an eruption. Indonesia, the Philippines, and other tropical volcanic regions might see increased lahar frequency as rainfall patterns change. Looking even further into the future, billions of years from now, Earth's volcanic activity will gradually decline as the planet's interior cools. The heat that drives plate tectonics and volcanism comes from two main sources: leftover heat from Earth's formation and heat from radioactive decay of elements like uranium and thorium in the mantle. Both sources are finite. Radioactive decay produces less heat over time as radioactive elements are consumed. Earth's interior is cooling at a rate of about 50 to 100 degrees Celsius every billion years. As the mantle cools, it becomes stiffer and plate tectonics will slow down. Eventually, perhaps 3 to 5 billion years from now, the mantle might cool enough that plate tectonics stops altogether. When that happens, volcanism will decline dramatically, though it won't stop completely. Some volcanic activity might continue for billions of years after that, powered by the remaining heat in Earth's interior, but volcanoes will become far less common and less powerful. But before that distant future arrives, we might face a supervolcanic eruption. Remember Yellowstone and Toba, the supervolcanoes we discussed earlier? These systems remain active today. The Yellowstone supervolcano has erupted 3 times in the past 2.1 million years, with the most recent eruption 640,000 years ago. That's a long time, but it's not unusual for supervolcanoes to have quiet periods lasting hundreds of thousands of years between supereruptions. Toba in Indonesia erupted 74,000 years ago in the largest volcanic eruption of the past 2 million years. It ejected about 2,800 cubic kilometers of material, creating a volcanic winter that may have lasted a decade and cooling the planet for centuries. Some scientists propose the Toba catastrophe theory, suggesting this eruption created a genetic bottleneck in the human population, reducing our ancestors to perhaps only a few thousand individuals. More recent evidence suggests the impact on human populations might not have been quite that severe, but it was certainly devastating on a global scale. The next supervolcanic eruption will happen eventually. Statistically, Earth experiences a VEA-8 eruption roughly every 50,000 years on average, though the actual intervals vary wildly. It could happen tomorrow, or it might not occur for another 100,000 years. When it does happen, the effects will be felt worldwide. A supereruption would inject so much ash and sulfur dioxide into the stratosphere that it would cool global temperatures by several degrees for years, disrupt weather patterns, damage crops worldwide, and potentially cause widespread famine. The good news is that supervolcanoes don't erupt without warning. Monitoring at Yellowstone is extensive, with networks of seismometers, GPS stations, gas sensors, and satellite observations. If magma began rising toward the surface in preparation for a major eruption, we'd almost certainly detect it months or years in advance. This would provide time to evacuate nearby areas and prepare for the global impacts. But preventing a supereruption is beyond our current technological capability. We'd have to adapt to the consequences. Beyond supervolcanoes, scientists are also studying volcanic eruptions as a factor in future climate models. Even moderate volcanic eruptions can have measurable effects on global temperature. A VEI-6 eruption, like Pinatubo, might cool the planet by half a degree for a few years. Multiple large eruptions in quick succession could have cumulative effects. Climate models that fail to account for future volcanic eruptions may underestimate the uncertainty in temperature projections and overestimate how quickly warming thresholds will be crossed. As you sink deeper into peaceful rest, imagine the volcanic story that spans from the beginning of our planet to its distant future, from eruptions that built the ground beneath us to eruptions yet to come. Think about volcanoes on other worlds. Mars with its ancient giants, Venus with its thousands of active vents, Io with its spectacular constant eruptions. Consider how something as seemingly unchanging as a mountain can actually be a breathing, living part of a planetary system shaped by heat from deep below, by tectonic forces we barely understand, by processes operating on timescales that dwarf human comprehension. Volcanoes remind us that we live on a dynamic planet, one that continues to evolve, continues to change, continues to surprise us. They connect Earth's surface to its deep interior, the atmosphere to the solid ground, the past to the future. And they'll continue their work long after we're gone, building new land, recycling old rock, keeping our planet geologically alive. Rest now, knowing that these magnificent forces of nature, for all their power and danger, are also builders, creators, essential parts of what makes Earth the remarkable living world it is.